Okay, well, let's recall what we did last week, and then we'll we'll prove what we stated last week and didn't prove. And abelian space, did we talk about abelian spaces or simply connected spaces? Well, let's say simply. Let's say simply connected. Anyway, we did prove the existence of a minimal model for simply connected algebras only. So the rank of the dual of the nth homotypic group is the dimension of the space of the space of generators of degree n. Basically, each mn is obtained from the previous one by adding some generators in degree n and specifying the differential on those generators. And we claim that the dimension of the new space of generators is the rank of the homotypic group. And we sketched a plan how to prove this, but let's see some more detail. firstly, let's look at the Leray spectral sequence for this vibration. By the way, what's the fiber of this vibration? Значит, у нас есть вибрация. Значит, n-ты теж Башня-Хойснікова росло над n, нет, n плюс 1 росло над n-том. Так спрашивается, какой слой? K pi n plus 1, comma what? N plus 1. Okay, well, by construction, we know that the space, all stages of the Postnikov tower are simply connected. So by construction, we have this, and so E2 PQ is equal to HP of xn with coefficients in HQ k pi n plus 1, n plus 1, comma q. Like this. Okay, does this formula make any sense? Has everyone seen this formula? Does everyone understand that this condition is important? And if we don't have if the base is not necessarily simply connected, then the same formula remains true, except here we have not necessarily the constant sheaf, but some locally constant sheaf. Which is the qth direct image of the constant sheaf, and it doesn't really matter for us at the moment. We only deal with simply connected spaces for the moment. Anyway. In the zeroth row, we have just the cohomology of the nth stage, and then what's the next non-zero row of the spectral sequence? Yes. We will only need this group E2 0. No, Yes, E2, 0, n plus 1. So what do we have here? E2, 0, n plus 1. Well, but by this formula, it's the same as h n plus 1 of k pi n plus 1 n plus 1 q. Okay, so what's this group? Yes, but how to express it in terms of pi n plus 1? No, not quite. Well, let's remember the universal coefficient formula. That's hom pi n plus 1 q. Now, my claim is the result is the same as hom over q, pi n plus 1 tensor q, q. And I think we sort of talked about this last time. So here we have pi n plus 1 tensor q dual. Does everyone agree? And we have some differential. Which is d n plus 2, I think. Okay. Now, we don't know what this differential is yet, but let's think about it. We have zeros in every row between these two. So by the group E2, 0, n plus 1, as a vector space is isomorphic to okay, let me write it like this. I think that this is the same notation we used last week. C plus K C plus K1, where C is the co-kernel the co-kernel of the cohomology map in degree n+1, and K is the kernel of the cohomology map and degree n+2. Okay, well, why? Let's look at this formula and see why it is true, if it is true. Так, ну, давайте сосредоточимся, это не бином Ньютона. Значит, we have a spectral sequence. And there is just one differential we are interested in. And it goes from this group to E0, E n+2 0, and we also have the cohomology map induced by this. The co-kernel in degree n+1 can only come from this group. What's the kernel in degree n+2? Well, the kernel is all those classes which are killed by this differential. There are no more differentials to kill any classes in degree n+2. Okay, so the kernel kernel of this the kernel of this differential is the same as the classes here, which do not come from here. Does this argument make any sense whatsoever? Did Vasya and Fedya do spectral sequences in the other course? Did they do the Leray spectral sequence? Well, this is a particular case, a very easy one. After all differentials have done their work, whatever remains in the zeroth row is the image of the cohomology of the base in the cohomology of the total space. Okay, after we take the image, something, when we take the image, something dies. What? Precisely the classes which are in the image of the differential. Так, а вот, значит, были какие-то задачки, там, значит, тоже фигурируют спектральные последовательности. Значит, смотрели ли участники, значит, задачки? Значит, и какие, значит, какая реакция? Какую реакцию, значит, это вызвало? Значит, спектральных последовательностей, к сожалению, нужно бить руку. Значит, нету какого-то такого универсального, значит, способа. Значит, там, к сожалению, нужно проделать несколько примеров. И, ну, вот, в частности, значит, один из способов проделать эти примеры, посчитать там первые гонотопические группы, там двумерные сферы. Далеко продвинуться таким образом нельзя. Но значит, понять, как, значит, что куда отображается спектральной последовательности, можно. Okay, so let's leave this as an exercise, but it's more or less straightforward from the spectral sequence. Значит, то, что остается в нулевой строке после пробития всех дифференциалов, это образ, значит, образ базы в тотальном пространстве. Значит, то, что остается в нулевом столбце после пробития всех дифференциалов, это что? Нет, нужно осторожнее с этим. Правильно. Значит, пробили все дифференциалы, значит, убили кого могли. Что осталось? Что осталось в нулевом столбце? Значит, смотрите, то, что остается в нулевой строке, оно всегда фактор. А то, что остается в нулевом столбце, в односвязанном случае, оно всегда значит, подгруппа. Что же такая за подгруппа? Значит, в когомологиях слоя возникает из расслоения. Нет, на когомологию, в другую сторону. Ядро какого отображения? А образ какого отображения? Какого? Значит, у нас слой отображается в тотальное пространство вложением. И вот, соответственно, когомология отображается в другую сторону. сколько гомологии тотального пространства отображает сколько гомологии условия. То, что остается в нулевом столбце, это образ из тотального пространства в слой. А про умножение они что-нибудь говорили в Свете?
Да.
Так, хорошо. Так, хорошо, нам сейчас это понадобится через секунду. Так, значит, понятно ли вот эти, значит, утверждения про спектральную последовательность, или это что-то из области там каких-то там заклинаний и так далее? Ну, значит, Сава, это, значит, нужно набить руку. Значит, нормально это не, значит, недостаточно, нужно набить руку в этих вычислениях. Okay, so let's briefly recall what we did last week. This space is precisely the space of new generators. For mn plus 1. Mn plus 1, what is it? It's mn times lambda of this space with some differential. Okay, now we basically have all ingredients. Suppose by induction hypothesis that we have constructed a map from Mn to to the forms on Xn. So, if we have a map from the nth term of the filtration on the minimal model, we get a map from the n plus into the co-chains of Xn. We can construct a map from the n plus first stage to the co-chains of Xn plus 1. How? Can anyone tell me by looking at this definition of n plus 1, can anyone tell me how to construct this map? Well, yes, but we need to be careful because this is just some group in the spectral sequence. So we we need to, but it is true that it suffices to specify the map on the new generators. Plus 1, yeah, okay. How do I specify the map on the new generators? There's one thing we need. Okay, hn plus 2 xn hn plus 2x, and same here. It's the co-kernel n plus 2 xn, no, n plus 1 xn, n plus 1 x. Basically, this is again straightforward from the spectral sequences. For example, here if we have a class in xn which vanishes in x, it must vanish in xn plus 1. Sorry, the co-kernel. If we have a class in x in hn plus 1 of x, it must come from it must be non-zero in hn in xn plus 1. So the all cohomology in degrees n plus 1 or less are the same for xn plus 1 and for x, immediate from the spectral sequence. basically look at this spectral sequence. Replace xn plus 1 with n. We see that anything new for xn, anything new appears in degree in degree n plus 1. Глядя на ту же самую спектральную последовательность гомологии в степени n и меньше, у x такие же, как у x n. Ну вот просто потому, что там в градировке n ничего не происходит абсолютно. Значит, это при переходе от n к n плюс 1. Значит, дальше при переходе от n плюс 1 к n плюс 2 тем более. Имеет ли смысл все вот эти вот рассуждения? В общем, я вот утверждаю, что вот конкретно вот это следует из спектральной последовательности, и вот это вот тоже следует из той же самой спектральной последовательности. Значит, если какой-то класс xn умирает в xn плюс 1, умирает в x, но не все xn отображаются в x, правильно? Если какой-то класс xn умирает в x, то он умирает в xn плюс 1. Потому что потом уже следующие дифференциалы с этим классом ничего не сделают. So both these equalities follow from the spectral sequence. Okay, so here we can use the kernel and the kernel of the map to the cohomology of xn plus 1 or the cohomology of x interchangeably. So we have this map. The C goes to the new classes which are missing in the cohomology of xn, but which are present in the cohomology of xn plus 1, and k kills kills the classes we don't need. So k goes to something which kills an element of k goes to something which kills a class here that must be 0. So using one of the questions from the problem sheet, don't remember the number, this this allows me to construct a map from the first from m plus 1 to the cochains on xn plus 1, and I need to prove that this map is an quasi-isomorphism. Okay. Now, how do I prove that this map is an isomorphism? We compare, we take two spectral sequences and we compare those. One is not surprisingly the Leray spectral sequence. There are several ways, lots of ways to construct the Leray spectral sequence. Okay, how do we construct the Leray spectral sequence? Which constructions do you know? Точные пары нам сейчас не помогут, к сожалению. Ну, в том смысле, что они, там все спектральные последовательности приходят из точных пар. Но нам сейчас, значит, это не жарко, не холодно, значит, фильтрация могут быть разные. Они все дают спектральные последовательности Ре, но они тем не менее разные. Так, хорошо, да. Значит, это, между прочим, ну, как ни странно, обобщается на гораздо более широкий класс примеров, чем могло бы показаться. Вот, но нам опять же, значит, это не очень сейчас полезно. Are there any other ideas of how to construct this thing? Basically, Sava mentioned two things. Firstly, we have the skeletal filtration, which gives the Leray spectral sequence after taking the brain images, and it's an important idea. It doesn't quite work in our example. Are there any more examples? Any more constructions? Well, for the record, there's another construction which is basically what we've already seen, namely the check construction. We can take an open covering of any open covering of the base, and the preimages form an open covering of the total space. Now, if the covering of the base we started with was a cyclic, then the resulting check complex gives us the ray spectral sequence. It's another source of examples. Does this help? Сейчас я не понимаю, какая фильтрация нужна, чтобы вот эти штуки были сравнимы. I need to think which. So we have this map, and we want to show that this map is an isomorphism by showing that it's an isomorphism on the spectral sequences. So I need to construct filtrations on both sides and prove that the spectral sequences are isomorphic starting from E2. Now, for this, let's leave this. Let's set this aside for a moment. For m+1, I do have the a sort of the ray spectral sequence. Namely, I just take the stupid filtration on M and tensor it with the new generators. The result is a filtration which is multiplicative. So we have the the E1 term, which is basically M tensor lambda of the new generators, and then the differential of this E1 is the differential in the differential in M. So we have the same E2 we have the same E2 as for the Leray spectral sequence, and we need to, we need to construct a filtration here, which gives such that this the map we've constructed is compatible with the filtrations. Итого, значит, у нас есть спектральная последовательность, спектральная последовательность. Мы знаем, что спектральная последовательность изоморфна. Значит, спектральная последовательность вот здесь приходит из некоторой фильтрации. Вот я хочу построить вот эту спектральную последовательность как приходящую из фильтрации, так что отображение переводит фильтрацию в фильтрацию. Значит, нужно придумать фильтрацию. So we need a filtration. We need the right filtration on this on this complex. Okay, so my my proposal is this. So let's call this map P, n plus 1 xn. Let's take the p forms on and also all forms of higher degree on xn. Take the pullback and generate the ideal. So this these brackets mean ideal generated by. Ideal inside the forms on xn plus 1. The pullback of an ideal is not necessarily an ideal. Okay, but we can take the pullback and generate an ideal. And my claim is the resulting thing will be will give us the Leray spectral sequence. Okay, so well, sorry, it's the same P. Let's call it F. We do want to have an ideal, and if we take two forms of degree 1, the product is of degree 2. Okay, so for the moment, this is a conjecture. Let's all think about it. Modulo this conjecture, we basically have the induction step for this argument. If we have a quasi-isomorphism on the nth stage, then we know that the new generators calculate the n plus first homotypic group, and then if we're able to prove that we have an isomorphism on the n plus first stage, then we can just continue. Okay, I will think a little about this conjecture. I don't know if I'm able to prove it or disprove it during the break. I'll let you know. Now, I also want to apart from this this statement. Are there any more comments or questions about what we've done so far? So let's summarize what we have shown. So by induction, we have shown that mn to APL of Xn is a quasi-isomorphism, and new generators for the n plus first stages, the nth homotypic group tensor Q dual. Are there any questions? I also wanted to say something about the minimal model for algebras which are not necessarily simply connected. But this time I claim nothing about the relationship to the homotypic groups, which is more complicated. So suppose such that we assume that the zeroth homology is Q, but the first homology is not necessarily zero. Let's see what happens if we use the procedure we talked about last time. We start with M1 to A. Where M1 is free. And the map we have straight away a map which induces an isomorphism in H1. But we have no control over what happens for H2. Now what do? We want to have an injective map in the second cohomology, but we haven't. So we have an M1 which maps into A, and the map may not be injective on the second cohomology. So we'll construct M2. Equal M1 tensor lambda of something. This something lives in degree 1, and it kills the kernel of the map from the kernel of the map of H2s, but it introduces maybe new elements of the kernel. So we continue indefinitely, or possibly indefinitely. We need to add some more generators, again of degree 1, to kill to kill again the kernel of the map M2 to A, and so on. What happens when we take the limit? Or more precisely, the inductive limit, the co-limit. When we take the co-limit, the whole kernel vanishes, and that's the trick. So the result is called the one minimal model. The key observation here is that when when I kill kernel in degree 1, I do not get new classes in degree. Sorry, when I kill the kernel in degree 2, I do not get any new classes in degree 1. So I do not mess up the fact that in degree 1 I have an isomorphism. So then we continue in the same fashion. And we get a minimal model indexed by omega squared, not omega, where omega is just the first infinite ordinal, viz. The natural numbers. Okay. Do we want to see in more detail how we proceed starting from here? Because I said and so on, and this was it. Хотим ли мы узнать, что происходит после того, как мы построили один минимальную модель неодносвязной алгебры? Значит, а что мы... Да, хороший вопрос. Давайте посмотрим. Вот, значит, что мы делаем? Мы добавляем какие-то один циклы, которые убивают, значит, то есть, значит, мы добавляем какие-то один к цепи здесь, который убивает ненужные два класса здесь. Значит, утверждение новых коциклов в градировке 1 при этом не возникает. Давайте это посмотрим более внимательно. So we want to understand in more detail why we do not get any new co-cycles one co-cycles in M2. M2 is M1 times lambda of some V, and the differential. So V lives in degree 1 and D the differential takes v to extra co-cycles in M1, extra 2 co-cycles in M1. The extra co-cycles are those which die in A. Those co-cycles are not co-boundaries of anything. So we have D. We have M1, 1. We have the differential which takes M11 to the co-boundaries, and we have an extra space V, and the differential takes it isomorphically to a complementary subspace. Of M1, 2. So those subspaces are both inside the degree 2 component of M1, but they are complementary. This construction does not add any new elements such that D of them is 0. We need to have a break, or else we'll get nowhere before we need to finish. Are there any more questions or remarks? Okay, I will try to think about the conjecture and the Leray spectral sequence during the break. Well, we'll see if I get anywhere. Okay. So regarding the conjecture, I think it's correct, but we need to give it justice. Let's talk next time about how to construct the Leray spectral sequence on the level of forms and how to construct it using using models. It's and how to compare the two constructions. It's an interesting topic. Let's talk about it. Well, probably next time. Now, I would like to state some ideas which are which relate to homotypic categories. On the other hand, we have QCDJs with quasi-isomorphisms inverted. And on the other hand, we have we have spaces which where we invert all maps which induce isomorphisms of the rational homology. Okay, let's not talk about let's not even talk about the homotypic groups because it's as we have seen, inverting maps which induce an isomorphisms of homology groups and of the homotypic groups with Q coefficients is the same for abelian spaces, and we actually don't even know how to construct the rationalization for non-abelian spaces. Well, there are several constructions, and the well, several means more than 3, less than 15. we do not want to go into this because it's not worth the effort. It's complicated and there are few applications. But still, we have these two categories, and we want to understand how the two are related. Ideally, we would have an equivalence between the two, but sadly, this is not the case. On the other hand, we have inside both we have let me erase what's on the right. We have two subcategories which are actually equivalent. The full subcategory in the first case is the one that contains all algebras which are connected and simply connected, and similarly in the second case we take all spaces which are connected and simply connected. And I would like to explain why these two subcategories are equivalent. So, in other words, if we prove this, then we will have reduced the study of this category to the study of this category, which is simpler. And the idea, how do we prove this? The idea is to to prove that both categories have what is called model structures, and there are two functors which in either direction there is a functor in either direction, and the two functors are adjoint. and those adjoint functors form a Quillen adjunction, and so as a result we get functors on the homotopy categories which themselves are adjoint. And then it so happens that the functor from topological spaces to algebras will be left adjoint, and the other one will be right adjoint. Then we can look at the subcategory of this category on which the junction is an isomorphism. Well, by general nonsense, this subcategory will be equivalent to a full subcategory of this category. And then we'll show that the first subcategory contains all spaces such that, and the second subcategory contains basically all algebras such that. And this will give us what we're after. So more precisely, the functor I would like to consider is some version of APL. APL is contravariant. So if I wanted to be if I want to be precise, I need to write an op here. So once we have this, we will have adjoint functors between the homotopy categories, and the unit of the junction on the homotopy categories is is an isomorphism for spaces with for spaces which are connected and simply connected, and secondly, we will prove that the essential image of the homotype version of the left adjoint functor contains contains all classes of CDGAs, such that H naught is Q, H1 is 0. Okay, so this is the plan. Well, to begin with, we need to understand at least something about all the words. So. By the way, if you want to see a down-to-earth, no model structures proof of the same theorem, then you could have a look at the book by Felix Halperin and Thomas. They try to use as little machinery as possible, and I don't remember the number of the chapter, but it's there. The advantage is obvious. One doesn't really need to talk about model structures and so on. Well, the disadvantage is the argument becomes sort of long, and we don't have time. We don't have time to look at long arguments, unfortunately. So we and besides, model structures are useful not only in rational homotypy theory. So it's something which is good to know if one is doing basically any kind of algebraic topology and or algebraic geometry. Although historically, the reason model structures appeared in the first place was rational homotypy theory. This was the first example that Daniel Quillen had in mind when he constructed his theory of model structures. Proving that that a model structure exists on a given category is usually very, very painful. We'll hopefully in a few weeks we will see one or two procedures for constructing a model structure, starting from a model structure on a simpler category. And basically, there are two or three examples in which the existence of a model structure can be checked by hand, meaning straight from the definition, and then one uses various tricks and contraptions to get model structures in other categories. So we will see one of those tricks in a couple of weeks. Well, probably in order for this to make sense, I would like to probably we would need to start by defining model structures. So let me say a few words about the definition, and then we'll next time we'll see in more detail what well, probably maybe not next time, but in a couple of weeks we'll see in more detail what model structures are and what one can do with them. The main example will need to look at would be the QCDJs and topological spaces. So I will write the definition, and then I will say without proof what the ingredients in both cases look like. So to begin with, let's assume that C is complete and co-complete in the weak sense that it has finite limits and co-limits. Do the words co-limits and limits make any sense? Okay, so on top of that, we require that there should be three classes, C, F, W. And elements of C are called co-fibrations, elements of F fibrations, elements of W weak equivalences. And these have to satisfy some number of axioms. Well, I'm the first property. All classes are closed under taking composition and taking retracts. Well, composition is and contain all identities. Well, the property of being closed under composition and containing all identities are straightforward. What about retracts? Well, let's see what this means. Suppose I have an arrow, and I want to define when this arrow is a retract of another arrow. This is the case. if there is a commutative diagram such that where, sorry, this is supposed to be an F, such that everything commutes. Basically, it's if we consider arrows as a category, then we just get the usual, we apply the usual definition of a refract. Okay. This is the first property, and the second property is the 2 out of 3 property for W. This means if if 2 of the 3 morphisms FG of the composition are in W, so is the third one. To state the next couple of properties, we need to define acyclic fibrations and cofibrations. These are those fibrations, respectively cofibrations, which belong to W. Suppose I have a commutative diagram. Then there exists a diagonal arrow which makes everything commute. if let's call this, the first one I, and the second one, the first vertical arrow I, and the second vertical arrow B. So if I is a cofibration. Okay, let me write it. If I is inside C, P is inside F intersected W, or I is is inside C intersected W, P is inside F. Please pay attention. I may have messed something up. So for those of you who know the definition, please check. Does this work? Is it the same definition as the one you're familiar with? And number 4, we every map can be factorized as an acyclic cofibration followed by fibration, P1 in F, I1 in CW, and P2 in FW, I2 in F, in C. Okay. Well, so far it's just a lot of conditions, and it's not clear whether or not these whether or not there are any examples which satisfy all those. Have I forgotten anything?
So Fishman now has if after the attractor G and G is a vibration or whatever that we do, that's all there.
Yes, well, this is number 1. Is there anything I've forgotten? Паршак, я ничего не забыл? Или, значит, это первое свойство. F, C, and W are closed under compositions and taking retracts and contain all identities. Ну, пока только в одну сторону. Значит, если значит, если у нас вот эта стрелка такая, вот эта всякая, то, значит, то существует диагональная стрелка. Но мы пока не требуем, чтобы, значит, что если, значит, если вот такая стрелка существует, то для всех вот таких, то, значит, то это фибрация. Okay, so it looks like I haven't forgotten anything except it's not clear from the definition that this actually corresponds to anything. Well, let's see some examples. Okay, well, let's start with topological spaces. There are, well, at least two model structures on topological spaces, and значит, только для конечных пределов, копределов. So suppose we have C equal top. Now there are two model structures. Well, at least two. So the Quillen model structure. In the Quillen model structure, W is precisely the weak equivalences. F is the class of all self-vibrations. And C is complicated. But for our purposes, it suffices to know that C contains all CW inclusions, meaning the inclusion of a subcomplex in a larger complex. And there is sometimes people would want to have genuine homotypic equivalences as weak equivalences. And there does exist a model structure with all homotypic equivalences with W equal to true homotypic equivalences. And this model structure is called the Strom model structure. We'll talk about it when and if we need it. Now let's talk about co-chain complexes and chain complexes. If we are in the unbounded case, it doesn't really matter. And again is as in the previous case, there are many model structures. And let's have a look at two of those. Okay, so there is the projective and injective, I think. And in both of those, the weak equivalences are just quasi-isomorphisms, and then for one of those, the one of the classes is simple, and the other one is more complicated, although tractable. And for the other one, it's the other way around. And I forgot which is which. So let me. Okay, so let me describe two model structures, and then we will see whether or not I've mixed up projective with injective. So in the first model structure, the cofibrations are simple. I take term-wise injective maps as cofibrations. Okay. Let me just put dots here, and then I will explain what those are. Okay, so in the first case, we have term-wise injective maps as cofibrations, and then I would like fibrations to have a split. I would like the fibrations to split. So I would need to either consider co-chain complexes which are bounded below, and take the co-kernel to be term-wise injective. Or I could take arbitrary complexes, and in this case, I would need to take a generalization of injective in the unbounded case. And similarly here. I would here the vibrations are easy, and the co-vibrations are sorry. I want the co-vibrations to split. So the idea is I want the kernel to be either projective, term-wise projective in the bounded case, or k-projective in the unbounded case. But let's see if I messed up these two things, and then we'll call it a day. So what do you think? Okay, let's try to look it up. Okay, projector. Okay. Okay, vibrations as projector. No, it's the other way around. So for the projective model structure, the vibrations are anyway. We'll talk about all this in more detail. We'll talk about this in more detail later. Okay, so the gist is model structures, there exist examples of model structures. We've just seen two basic examples, and there are more, and we'll see more examples in the future. Are there any questions? Okay, well, then next time we will talk about modeling vibrations. This is something we use today, but didn't really prove, and then we'll see. There is another thing which I want to talk about, applications to the mapping class groups, and if there are people who would want to know something about that, again, please let me know.